All right, welcome back to debate database development design for the RVCC, Raritan Valley Community College. I'm Dr. Larson, Ben Larson, your instructor here. If you're part of my class, if not, if you're just watching online, welcome. Please feel free to join along and follow our labs. Okay, this class we're working on chapter 3, which is about working with data. So let's go ahead and start and take a look. So what is data? All right, so from a purely statistical standpoint, data is discrete and continuous values. If you've taken a stats course, you'll learn about discrete and continuous values. Uh, Example, discrete are whole numbers or specific decimals, such as your age, you know, or an individual's report complete numbers. These are quantifiable figures, like the number of players on a team, staff count at a department, that kind of thing. Continuous data, on the other hand, is measured along the spectrum. It's miles per hour, quantities of rainfall. Rather than being counted, it's something that you think of as in a range. It's not really a thing. Because if you, yeah, okay, we'd sit there and say 55 miles an hour is the speed limit, but if you actually measured what you were driving down the highway, I'm sure you go above and below that throughout multiple times, whether you have to stop in front of somebody or it opens up and you got some room to go. So that's why that's continuous versus discrete. And again, this is purely statistical, where data really is only numbers. Okay, it really kind of exists in a numerical area, you know. So now in a database, data can be much more than numbers. It's various types, everything from text, images, audio, video. If your facial recognition software relies extensively on data sets of human faces, now they're all vectorized and placed into numbers, but that's what gets loaded in their faces. Uh, Now, although storing video is different than text, fundamental principles for organizing data are the same. So we just keep that going. So metadata. I'm not sure if there's a phrase some of you heard. You may have heard like metaphysics, depending on how many hippie places you hang out with, that kind of stuff. But meta literally means about something. So metadata literally means data about the data. So this is used by your relational database management system. Remember, SQL Server is your RDBMS. It's your database management system, not your database, okay? And this is used to better understand what the data is. There's all kinds of information you can have data about data. Example of the information you can have in a column would be, hey, if I have a column about birth dates, the metadata says, hey, that's a date. Or if I have a column that says name, and I've set it as a varchar with only 50 characters, the metadata says this can be a string up to 50 characters long, okay? Another example, I always say to look at, think about the photo you've taken in your phone. If you go and look at the details, you're going to see a file size, location, where it was taken, uh, where the file's stored, the time and date it was taken. Keep this in mind if you're trying to send a photo to somebody, trying to claim you're somewhere you're not. If they look, they might be able to find out where the photo actually came from. Okay, so metadata is collected by database, includes information like your data type, when was the data last added or deleted or edited, and what user interacted and where the data was currently stored. This is the magic of the RDBMS. Your database is nothing but dumb data. The RDBMS can tell you, with you turn on the logs, can tell you who the last person to log in that looked at your data was, who the last person who updated your data, who loaded your data, last time your data was loaded, last time your data was updated, if it was deleted, last time it was backed up. All that kind of information sits in the RDBMS and it's handled through the use of metadata. Okay, so again, another idea phrase you may have heard is called big data. This was very popular a few years back. In fact, it became such a buzzword I got like tired of hearing it. But big data does not mean large data set. Okay, we had data warehouses at my previous jobs that were billions of records, billions, and they are not big data because they're slow. So the data to big data, you must meet the following criteria known as the 5 V's: volume, the scale or the amount of data generated; velocity, the speed at which new data is generated and needs to be processed; variety, the different forms of data; quality, the accuracy of the data; and the value, usefulness of the data in creating it. Good thing to think of for big data, things like network logs, where you're trying to look through who's in your accessing your network, who's in there, that kind of stuff. Big data is social media, it's a good feed of big data. Everything, a lot of one idea to look at big data is to say, hey, is this once this data becomes old, once this data is an hour old, is it really meaningful anymore? I mean, is it really meaningful an hour later that someone's in your system? You should have been done with that already. So that's big data. So it's another big buzzword that gets pushed around, but it's not what most people think it is. I just kind of wanted to get that out there. Okay, relational data is when we're talking about typical datum, which is believe me, the singular for data. Data itself is a plural word. Stored in a relational database, one thinks of the following, okay? So text, like people's names, IDs, think of driver's license, passport numbers, or even like your student ID number. Booleans, true and false. Discrete numbers, number of students, and continuous numbers, temperature, measurement over time, that kind of stuff. Okay. So that's kind of what sits in a relational data. So relational data, I want you to think of stuff that can be stored in a two-dimensional format. So you have two dimensions and they store your relational data. So just much like an Excel file. Okay. So who uses the data? That's a big question you have to ask yourself as an architect. Who is behind who uses this data? Well, one of the big users is your business users. Marketing's use data to target the right audience. Sales, you leverage data to forecast trends, set goals. Accountants monitor all kinds of aspects of the operation through data, everything from assets to audits to management, that kind of thing like that. Healthcare workers, they use data, patient data all the time to improve treatment plans while training AI systems to enhance diagnosis. Law enforcement use crime data for resources all the time, from investigating crimes to predicting use of crimes and where we can probably put more enforcement in place. Education, schools rely heavily on student data, including test scores, behavioral evaluations, all that kind of stuff. So data is used in almost every professional environment out there. Okay. And so who are some of the people that use data? We're going to talk about. We're just discussing working with data right now. We're not getting too much into the management of it. Just so one of the main ones to think of first is your data analyst, also known as your BI professionals, business intelligence. Uh, these may or may not be your IT workers. A lot of these people, they come in from business sides, but they use data to derive insight from what's out there. They turn data into information. They use tools like SQL, R, and Python and make visualizations and dashboards for metric analysis. They typically work in the department they support. Then we have DBAs. DBAs, they're more of your IT organization. They're the guys, they're people that manage your databases, servers, who has access to them, that whole thing. They manage the backup solutions, all that kind of information on the side of it. So they very much are sitting in the back, your infrastructure side of this equation. Okay. Data engineers. And the data engineers, essentially, they are creating and maintaining the infrastructure for large-scale data processing. Through pipelines, they handle a lot of large data, and they move stuff from one side to the other at most of the time at close to real-time speed. If you get into software engineering, you're going to understand pipelines are what connect all these microservices, which most of your programs out there, like whether you're on the Amazon website or whether you're using, Microsoft Excel, it's not one program that's written. It's a bunch of smaller programs. That's how they write programs. They write these little small jobs, and they all talk to each other. And pipelines are what allow these things to send the data back and forth across there. And that's what your data engineers manage. So your data engineers are closer to a typical method become a data engineer. Normally it's a software engineer who learns about data. So they have a lot of software engineering type experience. Then on the other hand, we have data scientists. This is what I do. And we employ analytical techniques, and we use machine learning, which is the fundamental basis of artificial intelligence, to solve very complex problems and drive insight. Everything from AI to market analysis. We have to be very good at math, stats, and programming to do what we do. The old joke is a data scientist is someone who's better at statistics than any software engineer and better at software engineering than any statistician. Finally, we have the data architect, and that is kind of the basis of this course is the idea of introduction to data architect. I jokingly refer to my data architecture duties as being a data janitor. Because often, every time I seem to show up to a new department, they say, "Oh, here's our database," and it looks like somebody just took a bunch of Excel sheets and dumped them into a pile, and I have to spend days, if not weeks, digging through this pile and try to turn it into something meaningful I can organize. So just think of it, unfortunately, a lot of databases will become a junk drawer or a storage closet without some kind of idea of how to organize this data. And that's the job of a data architect, is to take this disorganized data and place it in some kind of structure that people can access and use. Okay. But it's not enough just to organize the data. You need to know what the needs are based on. These needs can drive an informed decisions about how you're going to build the data model. Because the data model is what we're really going to talk a lot about here in this class, is how we're going to build out the model that will become our database. Okay. So I'll talk about the three main types of databases out there, but this one we'll talk about first is your transactional purposes, also known as, I call it the cash register database. It's a very popular name for it. These are our OLTP. are online transactional processing databases, and they're designed to record transactions in real time for reliable processing, inventory control, all that kind of stuff. We'll definitely get into it. These are normalized into smaller tables that enhance integrity and writing speed. Something we'll definitely get into later. You're going to get sick of normalization, I promise. But that's the main purpose of these, is to enhance data integrity and writing speed. Whereas reporting, we use online analytical processing, or OLAP. And these are often referred to as data warehouses or data marts. Now you might hear the phrases data lakes, data lakehouses. They prioritize reading speed over transaction. These are denormalized databases, and they feature wide tables. And again, this will make a lot more sense once we get into normalization, but just so you know. And they're often used, one uses for them is dashboarding is typically used on top of OLAPs. And they provide you a structured display that enables you to monitor performance and trends effortlessly. If you go to any store and they've got a thing up there, next in line waiting, that's a dashboard. They have any kind of KPIs they want to measure up there, which for those who don't know, in case you're not a business major, a KPI is called a key performance indicator. And what those are is those are numbers people in the board or down below management is concerned about. A KPI could be something as simple as how many units did we sell this week, or how many units did we ship this week, or how many tickets are opened by the help desk department, and how quickly are we closing our tickets. Those are all KPIs, key performance indicators. Okay, that's the kind of stuff, your data analyst and your dashboard, and that's what that's responsible for. It's why we have these databases, so you can produce this kind of information to be read. Okay. Then we have machine learning modeling. And machine learning, for those who know, is the foundation of artificial intelligence. It is exactly kind of what it sounds like, where you are given, instead of training a model using heuristics. Now, heuristics is rules. So if I were to create a program that said, hey, if what's your age? And if you came back and I said, hey, if your age is greater than 21, then you can have a drink. If not, you can't. Well, I just set a rule. I set the rule. I picked 21 out of my head for whatever reason and put it down. Machine learning creates rules through the data. You don't, as a programmer, tell it that, hey, at 21 they can drink or not. You feed it a lot of data, and it figures out through the patterns what can and can't be done based on ages and that kind of stuff like that. So unlike regular forecasting, ML is an iterative process that you can keep feeding it new data, so you need to have it set up so the data can be easily fed into the system. And rather than having programmers set rules, it's also important the data be set in the methodology that the model needs. And you're going to find that every model has its own approach as to how it wants to see the data. But that's kind of beyond the scope of this class. That's just the idea to let you know that big feeding point to this world, all AI, is because it's being fed a bunch of data. All right, now just to end this off, we're going to go ahead into the history of relational data model. Okay, so this is just an idea of kind of what's out there, and the first one we look at is 1970 is really kind of the start. This guy E.F. Codd publishes the relational data model for large shared data banks. Okay, is introducing his relational approach to data storage, moving away from proprietary systems used by companies like IBM. Before this paper came out, every company had their own way of storing data. So if you went from working from Texas Instruments to IBM, you had to learn a whole new way of storing data, which I'm sure was a nightmare. Luckily, I wasn't alive in 1970, so I don't remember that. But in 76, when I was born, another paper came out, Peter Chen, and you're going to see his name later when we look into ERD designs. He released the entity relationship model towards a unified view of data. And this is an entity model relationship, which will all be based on. This represents what most modern database architecture looks like, okay? The relational database management system software suite facilitated, and then here's a history of facilitating the storage here. So the first one, 1976, release of Multics Relational Data Store. It's the first relational database released. 79, Oracle, now the leading RDBMS, was launched. In 60, ANSI and ISO formalized SQL for database interaction. Before then, SQL kind of had its own flavors. It still has kind of its own flavors, but they're not as far off from each other as they used to be. In 87, Fourth Dimension, the first RDBMS from Macintosh was introduced. In 89, SQL Server was released, quickly became popular. And 2006, the rise of big data leads to new technologies like Amazon Web Services and Hadoop for managing your much larger data sets. Okay, that's all for this class this week. Next, we'll be doing our SQL lesson, and then we'll get into our lab. Thank you very much.